In this video, let's discuss MOSFET scaling. So in hindsight, one of the reasons that I believe led to the success of the MOSFET has been one, its ease of fabrication and the relatively low cost at which device improvements were made. So let's take a very cursory and simple look at this process of MOSFET scaling. So for digital applications, speed and power consumption were always the major concerns, right? So as you went to newer chips, newer products, you want them to work at faster, you want the results to come out faster than the previous, and you want to burn less power when you're arriving at the results. So to achieve this, what happened was MOSFET dimensions continued to keep shrinking to reduce the capacitance at the logic node, since those were the primary reasons why which determined the speed of the digital circuit. So over the years, you've seen MOSFETs which started off initially as 10 microns and over the years have scaled into the nanometer regime and finally now into the angstrom regime. So reducing these dimensions led to doubling, and this is the infamous Moore's law, which was an observation which also provided impetus to push for higher and higher performance as products scaled over generations. So the initial scaling work, a lot of it was done in the late 60s, early 70s. Dennard proposed a scaling technique in 1974, which was a very simplistic way of maintaining the same electric field post-scaling. And while that worked for a few years and a decade around this time, it was eventually given up because these simple relationships do not hold as dimensions reduce. Multiple issues occur when we reduce the dimensions of a MOSFET, and each of them required more than a simple fix to get them scaled to the subsequent generation. So some of the issues were short channel effects, degradation in carrier mobility, hot carrier effects, gate oxide degradation and breakdown, band-to-band tunneling, and off-state leakage. So we won't go into each and every one of this in detail because that's probably for an involved device class. Since we're dealing with design here, let's quickly look at what scaling was and what happened over the years. So let's quickly look at short channel effects. So here's a transistor shown here, and what typically happens in a transistor, you have the source, you have the drain, you have the gate and the oxide, and in most cases when the transistor is switched off, that is when you've not applied a voltage at the gate, you might have a voltage at the drain. At this point, you want the drain and source to be essentially disconnected from each other. Now the drain, because it has a higher voltage than the source, tends to have a larger depletion layer when compared to the source. Now if I reduce the gate length of the device without changing the voltage, what happens is that the depletion layer of the drain sometimes can extend all the way to the source, and this is known as punch through. And when this occurs, there is essentially a large field that exists between the drain and source and a path for the carriers to go through. And so essentially you have a lot of leakage or a large current that flows through this sub-channel region. So remember here in this case, the current does not flow from the channel because the gate is switched off. But there is still a current flowing from the drain to the source because of the fact that electrons can move through this high field region. And so essentially what has happened in this case, we say, is that we have lost gate control, right? And this happened because of the fact that you reduce gate length without changing the voltages. So now to get this transistor back to healthy operation, what you need to do is increase the control of the gate with relative to the drain of the transistor. Right now, by just reducing the gate length, you have increased the effect of the drain on the channel, leading to the gate losing control. So the simplest way to do that was to reduce the oxide thickness. When you reduce the oxide thickness, that increases the gate field and essentially that pushes the depletion from the gate here, and that pushes the depletion from the drain back towards the drain. Also led to reduced voltages. So every time you scaled the device, every time you reduced the gate length, this process had to be repeated over and over again so as to maintain transistor performance. Now what happened as you kept scaling this gate oxide? So you kept reducing the thickness of the gate oxide, and as these thicknesses became close to the wavelengths of the electron in the lattice, this oxide no longer behaved as an insulator. What would happen is an electron in the semiconductor could easily tunnel from the semiconductor to the gate or vice versa. Tunneling is a quantum mechanical phenomenon, and what that means is a current exists when you reduce this thickness of the gate oxide to the orders of dimension of the wavelength of the electron. And so that time essentially the insulator, what you thought was an insulator. So one of the foundations of the MOS is that the gate is a voltage control terminal, and this voltage controls what happens in the semiconductor. Now if this oxide is unable to behave as an insulator, the gate no longer functions as a capacitive terminal. This happened in the late 2000s, and so in the early 2000s to this SiO2, which was the oxide in the dielectric, was replaced with a higher K material, something of the lines of hafnium dioxide, and this material has a dielectric constant, a relative dielectric constant much larger than SiO2, which means that for the same physical thickness you get a much higher capacitance, or in other words, you can make the physical thickness of the layer much thicker for the same gate capacitance. So that was able to essentially increase the thickness of this layer and prevent quantum mechanical tunneling. So today almost all technologies or all MOSFETs available in the market have a high K gate dielectric. So let's look at the impact of scaling on the MOSFET IV characteristics. So if we consider or limit ourselves to thinking about the MOSFET as a switch, if I plot IDS versus VG, remember a switch, you want the MOSFET to exist in two states, an on and an off state, because most of the time you're dealing with Boolean algebra of zeros or ones. So you want an ideal switch to look something like this. You want it to switch at say positive VGS, and you want it to go from zero current to very high current. Because it's a log scale, I've not been able to show the zero here. Now in reality, what does a MOSFET look like? Some of the best MOSFETs, as we saw in the previous video, have a subthreshold slope of 60 millivolts per decade, which means that the best MOSFET shows a turn-on characteristics which look something like this, that a sufficient voltage is needed at the gate to eventually turn on the transistor and then get high currents. Or in other words, if you want to switch off the transistor doesn't switch off instantly. The current slowly reduces and finally reaches a low value of off current. So now let's look at the impact. So here I've shown an IDVG and an IDVD. So let's look at what happens if I reduce the gate length of the transistor. So if I reduce the gate length of the transistor, what happens is that we all know that the gate length of transistor reduction leads to an increase in the drive current. While that increase does exist, there is a large increase in the off-state current of the device, right? Which means that now if you talk about an on-off ratio, if you talk about how good of a switch the transistor is, by increasing the off current, you've essentially created a switch which is not as good as the previous one. On the IDVD characteristics, or the output characteristics of the transistor, what you end up seeing is, even though the current goes up, you end up seeing saturation to be no longer a constant feature, rather you see a slope in the saturation current, and this is due to the pinch off that occurs. So to fix this, again you reduce the gate oxide, and what that does is that pushes the off-state current down while buying you certain higher current. But again, what has typically happened over the years is that it has not been able to match these two directly. So what ends up happening is the off-state current over generations has been creeping up. So the off-state current is no longer constant but has been creeping up, and the increase has been arrested because of the fact that you could change the oxide thickness for every gate length. And again, if you look at the output characteristics, by increasing the gate field, you can play around with the pinch off. Now, what has happened beyond gate oxide scaling? Obviously, the next step which happened in the late 2000s was transition from a planar MOSFET to a double gate structure, or the FinFET, or the tri-gate as we know it. And then of late, foundries have been transitioning to a gate-all-around structure where the channel is surrounded by the gate on all its sides. So as you see here, as you go from the planar to the FinFET to the gate-all-around structure, you see that the control of the gate has been increasing. So from a one-sided gate to a two-sided gate to an all-sided gate. And that increased gate control allows you to scale or reduce the gate length of the transistor. So let's quickly look at a few trends in MOSFET evolution over the last century. So as mentioned, the initial idea of the MOS dates back to the 1930s. And one of the primary reasons why MOS could never make it then to production, or the reason why the first transistor was built was a BJT in germanium, was because of the poor interface between the semiconductor and the gate insulator. And as you know by now, creation of the inversion charge and a charge that can move is essential for the MOSFET to function and actually get a current between drain and source. First MOSFET was made in the early 60s using an aluminum on silicon dioxide and silicon stack. Initial drive currents were much smaller than BJTs. The BJTs, or the bipolar junction transistors, were the workhorse of the day at that time. And another problem there was the VT, which was unstable due to the mobile ions present in the oxide. The square law model was developed in that decade. The next decade or two saw improved process technology, huge changes in process technologies, in the development of clean rooms, in the development of clean processing, wet cleans, etc., which led to better quality MOSFETs, leading to very high drive currents. So it was in this decade that the MOSFET drive current became better than the BJT. And so initially LSI circuits were made with PMOS, again because the mobile ion issue was less in the PMOS, but gradually were replaced by NMOS, primarily because the electron mobility in silicon is much higher than the hole mobility in silicon. This decade also saw the manufacture of ROM and RAM on silicon. Both these devices were based off the NMOS transistor. Polysilicon gate technology was also developed in this decade, followed by what was known as a self-aligned process, and both these were essential to get better MOSFETs. With polysilicon gate technology, you were able to get high temperature processing, so you were able to develop better junctions. And with the self-aligned process, you were able to get better overlap capacitances and hence a better MOSFET. This decade also saw extensive analysis and studies on short channel effects. A lot of theory was developed, scaling theory, for example. Analytical models for 2D MOSFETs were developed, and a concept of scale length was introduced, and this was critical as technology scaled in the 80s and 90s. The next decade saw impact of high field showing up in MOSFET. So hot carrier effects are nothing but gravitational effects that happen when electrons on holes come under the influence of high electric field. So scaling much faster than what the constant electric field scaling had proposed led to hot carrier effects showing up, and that led to the invention of the lightly doped source drain. Source drain junctions continue to reduce, again to reduce the short channel effects. Halo implants were invented to improve the off-state leakage. CMOS became mainstream in the 80s with an N plus poly for the NMOS and P plus poly for the PMOS. Both these again were for quick fabrication and were able to get low VTs for both the NMOS and the PMOS. To reduce the gate leakage, because gate oxide had scaled substantially over these 2 decades, Oxynitride was introduced in the gate oxide primarily for improved scalability. The other big invention in this decade was the invention of silicides to reduce the parasitic resistance in the source and drain, and this again improved the drive current of the transistor. SOI was proposed. SOI stands for Silicon-on-insulator. It is a different substrate than the bulk substrate, and it was proposed as a solution for active power reduction. A few foundries today do manufacture circuits on SOI, and that continues to be one of the options required for either fast circuits or circuits which have low power requirements. Physical scaling began to run roadblocks towards the end of the 90s, early 2000s. And so the early 2000s saw material improvements that came in. Process-induced strain by silicon germanium in the source drain for PMOS and tensile stress liners for NMOS were introduced to improve channel mobility and therefore maintain or increase the drive current in the transistors. Metal gate and high K also came into production in this decade, and that led to further improvement in MOSFET characteristics, primarily by reducing the gate leakage. The FinFET or the tri-gate technology from Intel came into production in the late 2000s, and that was a big game changer. Finally, over the last decade, what we've seen is FinFET technology continues to scale. There are huge changes in FinFET density to achieve the high drive currents needed. Gate-all-around structures are moving into production now with a couple of foundries promising that in the next year or two, and this again improves scaling and reduces off-state leakage. And there is a move, again because of the fact that overall MOS structures continue to not show the huge changes in drive currents or performance that was seen in the 2 decades past. There have been other attempts to improve system level performance by playing around with packaging and doing heterogeneous integration. To conclude, dimension scaling brought about almost 3 decades of MOSFET performance improvement leading to system performance. However, that scale was reduced in the early 2000s. Material and process innovation continued, keeping the device performance on the same trajectory, although these inventions ended up causing tweaks to layout and design. So all those parameters became important for a designer. The tri-gate or the FinFET was another big jump where a structural change was made to MOSFET. Again, this was a very disruptive change, and a lot of additional layout and design changes were needed to get this into production. So this was accompanied by a huge cost increase in both fabrication and design, but it was something which brought a few years of scaling. GAA and complementary FETs will continue this trend, but recent conferences and recent technology trends seem to indicate that technology might diverge substantially based on application. And over the last year or so, we've seen that implementation of hardware for AI, because AI seems to be a big driver for electronics now, hardware for AI will prove to be the next disruptor in this technology.